Anyway, with that background, let us now use as tiles translates and modulates of this window. So, what we do is to construct a continuum of the following kinds of dot products. We have a function x t belonging to L to R, and we have chosen a window V t. The short time Fourier transform of x t. So, the short time Fourier transform is abbreviated often by STFT. So, let us use this abbreviation now onwards. The short time Fourier transform or STFT of x with respect to v, as we shall call it, STFT of x with respect to v. So, we have two arguments, the function whose short time Fourier transform is being constructed and the window with respect to which it is being constructed. Now, this is essentially the set of arguments which determine what short time Fourier transform we are constructing. But there is also a pair of arguments for this transform, which are the translation and the modulation arguments. So, these are, I would call, the so called primary arguments of the short time Fourier transform. And these one should call the secondary arguments. To explain this idea of primary and secondary arguments, let us take for example the Fourier transform. In the Fourier transform, the primary argument is the frequency, the angular frequency, capital omega. The secondary argument is the function whose Fourier transform is being calculated. So, when you calculate the Fourier transform of x t, the secondary argument is the function x. The transform is the whole operator. It takes this function x as a secondary argument and the primary argument is the angular frequency. So, with that little explanation, let us go back to the short time Fourier transform of x with respect to the window v evaluated. This is how we would read it. The short time Fourier transform of x with respect to the window v evaluated at the translation tau 0 and the modulation omega 0. Let us write that down. It would be essentially a dot product of the following. A dot product or inner product of x t with v translated by tau naught and modulated with e raised to the power j omega naught t. And how would this dot product look? Let us write it down. X t multiplied by v t minus tau 0 bar e raised to the power j omega naught t bar dt. And if you please, we could simplify this. Now, a couple of words here. if V t is a real function, as we have been considering all this while, whether it is the Gaussian or whether it is the raised cosine or the triangular function, or if you like the extreme case of the rectangular window, this complex conjugation is redundant, it is not required. If you look at it, what we are doing here in an alternate sense is to first multiply x t by a window appropriately translated. So, tau 0 is the location of the window. Essentially what we are trying is to extract information of x t around the point t equal to tau 0, and then we are taking a Fourier transform. That is another way to interpret this. So, short time Fourier transform is essentially a process of piecing or breaking the function into pieces, followed by a Fourier transformation. Here we are assuming a continuous tau 0 and a continuous capital omega 0, and therefore, we are talking about the continuous short time Fourier transform. Now, let us invoke Parsifal's theorem to get a different perspective on the same expression here. So, let us go back to the expression here. We have taken a dot product of x t with a translated version of the window and then a Fourier transformation on this product. So, for example, if V t were to be a triangular window, essentially it would extract the information of x t around the point tau 0 with some weighting done by the triangular function or the rectangular function. In the rectangular function, there is no weighting. In the raised cosine or the triangular or the Gaussian function, there is a weighting, different weights given to different points around tau 0, followed by a Fourier transformation. So, looking at the frequency content in a certain region. Now, if we invoke Parsifal's theorem on this, what does it give us? Parsifal's theorem says this is also the inner product of the Fourier transforms of x and v translated by tau naught and modulated by capital omega naught. Therefore, we need to calculate the Fourier transform of this quantity. That is a task that we need to do. The Fourier transform of V t minus tau 0 e raised to the power j omega naught t can easily be seen to be the following. So, it is minus to plus infinity V t minus tau 0 e raised to the power minus j omega naught t multiplied by e raised to the power minus j omega t integrated with respect to t. Now, let us simplify this. So, of course, we employ the standard process of replacement of argument. So, let us replace the argument t minus tau naught. And noting that for a fixed tau naught, when t runs from minus to plus infinity, lambda also runs from minus to plus infinity. This would become integral from minus to plus infinity v lambda e raised to the power j. Now, of course, collecting terms, this is omega naught minus omega times t, which is lambda plus tau naught d lambda. And now, of course, we have a simple answer there. We can rewrite this a little bit, taking out common terms. So, you will notice that when we expand this product, we have the term e raised to the power j lambda naught minus, or rather omega naught minus omega times tau naught, and e raised to the power j omega naught minus omega times tau naught is independent of lambda. So, I could bring it outside the integral. So, I am saying this becomes e raised to the power j omega naught minus omega times tau naught and the rest of it inside. And now, let me see what remains inside. What remains inside is V lambda e raised to the power j omega naught minus omega times lambda d lambda. So, let me write that part down. So, now here I shall write only the integral, I have left out the other term. That integral is essentially V lambda e raised to the power, I will rewrite it as minus j omega minus omega naught times lambda d lambda, which is easily seen to be the Fourier transform of V, but evaluated at omega minus omega naught instead of at omega. So, all in all we have the following. We have the Fourier transform of V t minus tau naught e raised to the power j omega naught t is the Fourier transform of V evaluated at omega minus omega naught multiplied by e raised to the power j omega naught minus omega times tau naught. And we shall substitute this in the Parsifal's theorem expression. So, we have the short time Fourier transform, secondary arguments of x with respect to the window V evaluated at tau naught and capital omega naught is essentially the following inner product with a factor of 1 by 2 pi, remember. So, it is x cap omega V cap omega minus omega naught e raised to the power j omega naught minus omega times tau naught d omega with this all complex conjugated. And let us simplify that, and once again let us note that when we expand this we get two terms, e raised to the power j omega naught tau naught and e raised to the power minus j omega tau naught, out of which only the second depends on capital omega, the first does not. So, the first can be brought outside the integral. So, what we have in effect is e raised to the power minus j omega naught tau naught times the following 1 by 2 pi, just a constant, x cap omega v cap omega minus omega naught e raised to the power j omega tau naught d omega. This is complex conjugated here. Here the complex conjugate has been taken care of as it is. And now we have a very beautiful interpretation for this. This looks very much like an inverse Fourier transform, if you think about it. It is the inverse Fourier transform evaluated at the point tau naught. Inverse Fourier transform of what? Of the Fourier transform of x multiplied by the Fourier transform of the window shifted to lie around omega naught. So, now this makes a lot of sense. The short time Fourier transform, as we expected, has an interpretation, a very similar interpretation both in time and frequency.